December 17th, 1976. A quiet evening at the port of Los Angeles in San Pedro, California, was about to be shattered by an unexpected disaster. The Sansanina, a Liberian oil tanker, had just unloaded a cargo of 212,000 barrels of Indonesian crude. Her Italian crew then filled the empty cargo tanks with seawater. This is a routine practice called ballasting. It keeps the tanker riding low in the water on her voyage back at sea.
About 7:35, somewhere along there in the evening, as I looked out that window, a tremendous pressure wave hit us.
I thought somebody dropped the bomb. It sounded just like I looked out the window and a big mushroom going up in the air. And I grabbed the fire phone, but it was dead. Everything had been cut off.
The force of the blast could be felt 40 miles away. In response, some 200 firefighters raced to the pier.
The first thing we saw when we arrived on the scene was a large mass of fire involving the wharf to such an extent that you couldn't identify what actually was out there. It appeared to me that there was a large building there on the wharf that was on fire, and yet I knew that there was no building there of that size.
The building Dahlquist thought he saw was a chunk of the 70,000-ton Sansanina. Part of its midsection had blown out of the water and landed in the parking lot. The rest lay submerged at the bottom of the harbor.
There was fire on top of the water, there was fire on the wharf, there was fire on the land. We simply worked all of those areas with our monitors until we were able to extinguish the fire.
Remarkably, most of the 30 men aboard the Sansanina survived the initial blast, but they were still trapped in the ship's burning remains. Firemen like Walter Ball risked their own lives maneuvering a fireboat through the flaming debris to reach the men.
About the first five, all of them they wanted to do was go, let's get out of here. They thought it was going to explode again. It was making all kinds of noises in the ship.
But Ball would not move until the last of the 18 men he had found clambered down from the ship's stern. In the end, more than 50 people were injured and 9 people were dead, including 3 men whose bodies were never found. The cause of the blast that claimed their lives and wrought so much destruction was a mystery.
Accidents are generally caused by a series of small items which fall into alignment, and it appeared that's what happened on the Sansanina that day.
The Coast Guard immediately launched an investigation into what caused the 18-year-old 70,600-ton ship to explode. They focused on what the Sansanina crew was doing prior to the disaster: ballasting. Depositing seawater into the same tanks that just unloaded oil could have created combustible fumes.
Well, in a tank, if you start to fill the water, of course the water goes to the bottom of the tank, and what it does is it forces the fumes out the top of the tank. Most hydrocarbon fumes, like gasoline fumes, are heavier than air. So what that means is when they get up, they don't readily dissipate up into the air. It sits there until it's driven off by the wind or something of that nature.
But on the day of the explosion, there was no wind, and the highly flammable vapor cloud was trapped between the midship deckhouse and the aft castle.
Well, if you have a huge volume of hydrocarbon mixed with air and you ignite this, what you have created in reality is what we call now a fuel-air bomb. And the effect, of course, can be devastating.
What caused the vapor cloud to ignite will perhaps never be known. There were too many potential sources.
Once you have hydrocarbon gas in the right ratio of fuel and air to be ignited, it will find an ignition source sooner or later. Trust me, on an industrial system, there'll be an electric spark, there'll be something being hot, and it doesn't take much energy to kick this off. It isn't just what collects on deck, that's what causes and finds a source of ignition. There were conduction paths of air-fuel mixtures down into the tanks.
The safety and ventilation systems on the Sansanina to prevent fire from reaching the cargo tanks were ineffective.
The flame screens are intended to prevent any flame from going into the cargo tanks on the ship. That was an industry practice at the time, and it appears they were not in place. It also appears from the Coast Guard reports that some of the gas lines which were intended to carry gas vapors away to safer areas may have been rusted.
Had the vents not been so rusted, they might have had a flash fire on deck, but they may not have had the big explosion of the ship. But all these things came together that day wrong, so a number of people died.
In 1977, almost a year after the accident, the Coast Guard completed their investigation and issued a report. Their analysis of what happened had far-reaching effects in the maritime industry. Today, there are significant safety features on tankers to prevent what happened to the Sansanina. Foremost are inert gas systems.
The theory is that by having no oxygen inside the cargo tank, it will not support combustion. If there is insufficient oxygen, there is no possibility of an explosion or fire.
A typical inert gas system involves taking gases from the ship's boilers and feeding them into the cargo tanks. This drives out all the oxygen. Without oxygen, vapors left in the tank are inert and therefore not combustible. Even though inert gas systems were in use in the 1970s, there were no requirements that the Sansanina have one. Today, no supertanker operates without one. In addition, venting systems are more sophisticated, so that hydrocarbon vapors are expelled high above the ship and unlikely to pool on deck. Ballasting is still routine, but modern tankers no longer mix oil and water. Ballast tanks are separate from cargo tanks.
If you look at the major disasters in history, you see in retrospect a sequence of mistakes, each one of which at the time appeared to be innocent and inconsequential, which all combined in a very unfortunate way at the time of the disaster to create a disaster.
It took an 18-year-old ship called the Sansanina and a horrific accident to expose dangers that stalked oil tankers at sea and at rest in quiet harbors. March 2nd, 1973, a Fairfax County, Virginia apartment complex was nearing completion. But in the middle of construction, disaster struck when one of 4 structures making up the tower collapsed, killing 14 people.
My initial reaction was, what in the world would make a building that's already gotten up to the 24th floor all of a sudden come tumbling all the way to the ground? And I confess, I had absolutely no idea, and no theory at all.
The job of determining the specific cause of the collapse fell to E.V. Leindecker, structural engineer with the National Bureau of Standards and Technology. Leindecker went to work to determine if the tragedy could have been a result of poor design. He saw no immediate shortcomings. The most important evidence came from workers at the site who survived the collapse. From their eyewitness reports, he was able to piece together a scenario. His conclusion: the collapse began shortly after a portion of the 24th-story concrete floor slab had been poured. At the same time, wooden forms used to cast vertical concrete pillars were being removed 2 floors below. According to engineering design recommendations, those forms were removed too early.
The engineer's drawings had a statement on them that indicated that under a floor being cast, or where the concrete was being poured, that you had to have a complete farming system. That means the wood that's supporting the concrete had to be in place underneath the slab being cast, and also had to be in place for 1 story below that.
The wet concrete being poured on the 24th story did not have enough support because wooden forms were removed on floor 22, where vertical concrete pillars were not completely cured. Within days of the collapse, the question became not what happened, but who was responsible for carrying out the instructions stated on the engineer's drawings. Fairfax County building inspectors were not required to inspect the curing of concrete before additional floors could be constructed. It was the job of the contractor to make certain that vertical columns were secure before concrete was poured for the new floors.
I could visualize people going in and pulling farms, and I say, hey, we're great, making good progress, let's just keep on going. That's always been one of my own conjectures, but that's all that is. But I think it probably was the inappropriate level of communication between the people running the construction site and the actual workers that were executing the work, but maybe not having explicit instructions on what they should be doing.
When it became obvious that the skyline collapse had been the result of poor engineering supervision, the Fairfax District Attorney's Office mobilized to determine if any individuals were criminally liable.
We ultimately presented a case to the grand jury to charge the superintendent of construction on that day. We charged him with manslaughter for what we perceived to be a willful, wanton disregard of human life, and a jury was never able to resolve it. The result of the trial was a hung jury, so there was no conclusion criminally.
The Skyline apartment complex was completely torn down and rebuilt. The collapse made an impact on building inspectors locally and across the country.
In the months after this happened, it seemed to me every high-rise building in the county under construction had 3 floors of shoring in place at all times. I think this scared the industry. It resulted in much more concern about safety than maybe had existed before.
Today, as a direct result of the Skyline incident, building codes and contractor safety guidelines are more defined and enforced. No city wants to experience anything like the Skyline Plaza engineering disaster. November 10th, 1975. The 29 crew members of the 729-foot ore carrier, Edmund Fitzgerald, were fighting an intense storm on Lake Superior. Their destination that day was Whitefish Bay, on Michigan's Upper Peninsula.
We're at Whitefish Point, just in front of the light station. Today the winds are only about 20 miles an hour. Can you imagine what it would have been like with 96-mile-an-hour winds? These waves are only about 4 or 5 feet today, but they were 35 feet back in 1975.
Despite the raging storm, the crew was confident in its safety. The Fitzgerald was one of the strongest and most capable ships on the lakes.
This was a big, powerful boat, and people really wanted to be on the Edmund Fitzgerald. This was the one you aspired to serve on.
In fact, when it was launched in 1958, it was the premier ore carrier on the Great Lakes, setting records for the largest loads carried and the fastest trips. Captain Ernest McSorley was also one of the most experienced in the business, with 44 years of sailing on the Great Lakes. But on this day, McSorley was virtually blinded by 2 critical navigational system failures. His first obstacle was the failure of both radar units, a problem he reported to the nearby ship, Arthur Anderson. To overcome the loss of radar, the Fitzgerald tried to use Whitefish Point's radio direction finder, but the storm had knocked out its power, rendering it useless. At about 3:30 in the afternoon, McSorley reported to Cooper that one of the fence rails, part of the sturdy safety fences on each side of the Fitzgerald, had snapped. He also said 2 vent covers were missing, and the ship was listing to the side, evidence that water was entering the Fitzgerald. These were all signs of severe damage, but the ship soldiered on, pumping out water as it went. Then at 7:10 p.m., the first mate aboard the Arthur Anderson asked McSorley about the state of his crew.
The response back from Fitzgerald to the Arthur Anderson is, "We are holding our own." That was the last communication between the 2 ships.
Minutes later, the Edmund Fitzgerald disappeared from the radar screen aboard the Arthur Anderson without as much as a distress signal. After a difficult and limited search during the storm and a larger search the next day, it was clear the unthinkable had happened.
It looks from the information that we have that it's fairly certain that the Fitzgerald went down, and we're talking now about a matter of life and death and looking for survivors that might be in life rafts or in the water.
The massive Edmund Fitzgerald and her crew of 29 men were gone.
We can only ask the masters to...
6 months later, the cameras of a remotely operated U.S. Navy submersible spotted the wreckage, agonizingly close to safety, just 17 miles from Whitefish Point. Those first images of the wreck, and footage from many other dives over the years, showed that the ship lay in two pieces on the bottom of Lake Superior, with its back, or stern, resting upside down. But locating the wreck did not solve the mystery of how the ship sank and why the crew never called for help. More than 3 decades later, strong opinions still surround the theories of the ship's tragic fate. A Coast Guard investigative board looked into many possibilities. Probably the only one that they could confidently rule out once the wreck was discovered was the possibility the Fitzgerald had broken in half on the surface.
The ship didn't break in half because the bow would have floated for a while longer and the stern would have floated for a while, and they both would have disappeared a little bit further apart.
Instead, the two pieces of the ship lay only a few hundred feet apart. In terms of official findings, the Coast Guard report issued on July 26, 1977, concluded that water crashing on the deck and leaking through cracked and poorly sealed hatch covers was the most likely cause of the disaster. The seals on freighter hatch covers were often damaged during loading and unloading, and crews often skimped on the tedious process of tightening most of the hatch cover clamps. Still, many people disagreed with the Coast Guard's theory.
If water was leaking in through the hatch covers, then the pumps that were on, these 7,000 gallon per minute pumps, and there was 2 of them going, should have been able to keep up with as much water that these hatch covers would allow through leaking.
The Lake Carriers Association, which represented 15 shipping companies, protested to the National Transportation Safety Board, which issued its own findings on May 4, 1978. The NTSB also focused on the cargo hatches, but in a different way. It felt the tremendous weight of the water crashing across the Fitzgerald's main deck, known as the spar deck, forced one or more of the hatches to implode and swiftly flood the cargo hold.
You can tell by the size of these things, this 729-foot freighter, these things weigh tons, and it would take an awful lot of weight to cause them to implode.
Finally, the Lake Carriers Association proposed its own theory, that the Fitzgerald struck bottom in the shallow waters around Caribou Island, a plausible consequence of the ship's navigation system failures. Hitting bottom could have caused a rupture in the hull below the waterline. The downed fence rail and missing vents that McSorley reported near Caribou Island seemed to support that scenario.
This was serious. How serious? Not serious enough that McSorley thought he couldn't continue on. He had his pumps going. He thought he had it under control. But it's serious when a fence rail comes down. That indicates an incredible change in tension in the hull itself.
The type of tension that could result from the middle of the 729-foot ship hitting bottom.
And if you hog a ship, meaning cause it to bend up in the middle, you can stretch those cables and cause them to snap because they're supported with stanchions all the way along. Something's got to give.
But since there are no scrape marks on the portion of the hull wreckage that can be seen, bottoming out, like the other explanations, remains just a theory. However, most theories at least agree that the Fitzgerald was taking on water faster than it could be pumped out. And the more water that came in, the lower the ship would ride in those high seas.
The waves were actually boarding the Fitzgerald on the starboard quarter, rolling the full length of the deck, the spar deck, and hitting the back of the pilot house and actually forcing this 40-foot high structure underwater, and it would come back up and shake the water off the deck and keep going. But one of those dives that did under one of these huge waves was the final dive, and it just kept going 535 feet to the bottom.
If McSorley believed the ship would resurface after that final wave, then the first sign of trouble, and the last, would have been a wall of water bursting through the windows of the pilot house from the increased pressure of deeper waters. This would explain why there had been no distress call. But there's still no single theory about the tragic fate of the Edmund Fitzgerald that will satisfy everyone. The bodies of all 29 crewmen remain entombed in that watery grave. And at the request of their families, divers are no longer permitted near the wreck. But those relatives do have 2 special places where they can remember loved ones. Just outside the Dawson Great Lakes Museum in Detroit, an anchor that belonged to the Edmund Fitzgerald prior to its last voyage is displayed. And at the Great Lakes Shipwreck Museum at Whitefish Point, the original bell from the Edmund Fitzgerald is the centerpiece of the collection. Known as the voice of the ship, It was recovered from the wreckage at the request of the families on July 4th, 1995.
When this bell broke the surface after 20 years of darkness and silence, it actually swung and tolled, and everybody around for about a mile could hear it. It was one of the most eerie experiences I've ever had, and the tone itself has such a resonating quality to it that is something that you'll never forget.
Buffalo Creek, West Virginia. Civilians in the surrounding area of Logan County tried to escape, but the powerful torrent turned fatal. 125 people died, and over 1,000 were injured in the devastating tragedy. Logan County was one of the most prolific producers of coal in the United States, but its history is now linked to a deadly engineering disaster that forever altered life in the coal mining community. Coal mining has always been a dangerous activity. Methane poisoning, cave-ins, and explosions are just some of the hazards that plague miners. Over the decades, hard-fought gains in safety conditions and increased automation made coal mining a somewhat less hazardous job. But one aspect of the coal mining operation remained dangerously unchecked: coal waste dams. Unlike traditional dams, coal waste dams provide neither electricity nor a reservoir of potable water. They are essentially gigantic garbage dumps.
You mine coal, and coal usually has some material in it that's not coal. You run it through different processes, and you end up with coal, and then you end up with refuse. And these processes include the use of water. So now you have refuse you have to get rid of, and water you have to get rid of.
For years, mining companies dumped the wastewater directly into streams, including Buffalo Creek. But early environmental laws stopped that.
Companies were required to at least make an effort to try to control the wastewater from the plant. The cheapest thing for them to do was just to build a dam across the valley.
In 1960, the Laredo Mining Company built what became known as Dam Number 1, overlooking the narrow valley of Buffalo Creek. The dam was built of coal waste, also called gob, which smoldered and often caught fire due to its high carbon content. When Number 1's reservoir became filled with silt, the mining company built a larger dam, Number 2, right behind it on soft clay soil, with little shear strength. Several problems plagued the first two dams.
Dam Number 1 overtopped several times, and there were black water discharges that came into Buffalo Creek. Dam Number 2 failed. The front face of it failed and split in the middle a couple of times in the late 60s.
The U.S. Geological Survey reported that the dams were vulnerable to a washout.
There was evidence of foundation failure piping in both structures, and particularly in Dam Number 2. But the company went ahead and built the third dam anyway.
Dam Number 3 was to be massive, 500 feet thick in the middle, stretching 465 feet across the valley, and rising 60 feet above Dam Number 2's impoundment pond. And the fact that it was to be built overlooking a floodplain, home to several small towns. The only engineering plan was this rudimentary sketch. At the time, engineering requirements for coal dams and federal enforcement were sorely lacking.
There was just one provision that said any refuse embankments and impoundments should be substantially constructed. That was it, one paragraph.
Bulldozers began forming the giant face of Dam Number 3 in 1968.
The coarse refuse material was not compacted. It was dumped by large trucks and then pushed into the center of the valley, out on top of the slurry that had been discharged by the previous dams. There's no way one could get compaction with that thick a layer of material being pushed forward. So there was no strength whatsoever in the material.
In addition, the dam was built without proper spillways to alleviate the reservoir when it reached capacity. Such basic engineering deficiencies made a catastrophe virtually inevitable.
The front face of the dam failed, I believe, in 1969 and again in 1971. So there have been two failures of the front face of Dam Number 3.
prior to February 26, 1972. Anybody with engineering knowledge knew that there were some serious problems with dam number 3 and its long-term stability.
Despite such evidence, the Pittston Company, the dam's final owners, did not make the needed structural changes. 8 a.m., February 26, 1972. 4 years of runoff from the mine and seasonal rains had swollen the dam's reservoir to 132 million gallons. Anxious residents noted large cracks in the dam's face. The crest had softened.
The mining company officials, even though they had no real engineering knowledge, took it upon themselves to tell people that there was no danger and they should go home or stay in their homes. And it was only some local residents who actually warned their neighbors and got some people out.
Somebody did call my mother and told her that there was fear, I guess, up on the creek that the dam would break. So we kind of knew something was going on. We didn't have any clue how bad it was going to be, though.
Water had saturated so deeply into the dam's interior that a third of its face slid off into the impoundment pond of dam number 2. The remainder of the dam then failed catastrophically. It simply liquefied, unleashing massive amounts of energy as it overtopped dams 1 and 2 on its unstoppable path to the valley below. The flood announced itself with loud explosions as it slammed into the smoldering gaw pile that was dam number 1. The town of Saunders was directly below.
Within a matter of moments, the whole town of Saunders was obliterated by this mass of water and slurry.
The 20-foot-high floodway surged with 132 million gallons of water and 1 million gallons of sludge. It gained momentum from gravity and from its own increasing mass as it grabbed up mud, coal waste, and soon, houses and cars.
I could see the creek and I could see all this black water coming down it and thinking we got some type of flood. And then I seen that white house float down and hit the bridge. And, you know, the house just splintered all to pieces and the water backed up and started coming over toward where I was at.
As some scrambled up the cold, muddy hillsides to escape, they looked back to see houses floating by, with people still looking out the windows. These houses were soon smashed to bits along overpasses and railroad trestles.
When the trestle started breaking, I heard a lot of people screaming. And we found out later that there were people on the trestle when it broke.
The torrent of water and waste cut a 17-mile swath of destruction through the 17 small towns along Buffalo Creek before joining the Guyandotte River. It was all over by 11 a.m. 125 people died. 1,000 more were injured. 507 houses, 44 mobile homes, and 30 businesses were destroyed. 4,000 people were left homeless.
It was like you had civilization one day, and then it was pure chaos the next day, and that chaos lasted for a very, very, very long time.
Entire families died together.
There was friends and friends of friends and relatives of relatives that died. A lot of funerals to go to.
Rage followed grief.
Co-operators' money and elect you politicians, and you get to Washington and you care nothing about it.
As with other disasters of this scale, the Buffalo Creek Dam disaster was a shocking wake-up call to federal and state agencies. The Army Corps of Engineers and the Mine Safety and Health Administration, or MSHA, launched a comprehensive inspection of coal waste dams across the nation.
We felt that we needed to have an engineering analysis of what was available and be able to tell the mining community, if you're going to build these things, here's what you got to do.
Out of the horror of Buffalo Creek came a remarkable era of dam improvement where before almost no regulations existed. MSHA and other agencies wrote detailed engineering specifications. They demonstrated how proper engineering, combined with vigilant public scrutiny, can December 22nd, 1977. It was just after 9 a.m., a quiet morning in the small southern city of Westwego, Louisiana, when suddenly, a 250-foot grain elevator exploded.
It was heard by people over 10 miles away from the facility. The energy released in this explosion was equivalent to many hundreds, if not thousands of pounds of TNT.
There was fire and smoke coming from the tops of the silos. There was debris everywhere. It was total devastation.
Even more shocking than the magnitude of the explosion was its cause: grain dust.
Any material that can burn will burn rapidly and explosively if it's small enough. Grain produces dust when it's handled. That dust burns so rapidly, it's explosive.
And when fine dust particles are suspended in air, surrounded by oxygen, the mixture becomes highly volatile. Because of their design, grain elevators are highly susceptible to dust explosions. The actual elevator at a facility typically consists of a multitude of buckets connected to a vertical conveyor belt. When a barge is unloaded, the bucket elevator scoops up grain and carries it to the head house. From there, it's sorted by grain type and dropped into concrete silos.
Grain elevators are designed to move tremendous quantities of grain. When you handle these materials, the generation of dust is inevitable. If you look at the 4 factors required for a dust explosion, the presence of dust is ever present. We have enclosure or confinement of the structure itself and oxygen in the air. Therefore, all that's needed is a spark or ignition source to have a dust explosion.
On the morning of December 22nd, an unusual cold front was passing through West Wego, dropping the humidity to a very low level. Both static electricity and grain dust were in the air, making the unthinkable possible.
About 9:15, I heard an explosion, and my daughter and I went up to the river road. All we could see was a lot of dust and a lot of concrete all over the place.
There were people walking around covered in grain dust. Many of them were digging through debris trying to find co-workers and things like that. Helicopters were there probably within 30 to 40 minutes after the blast, and they were trying to rescue people off the tops of the silos.
The radio said it was the river side of the grain elevator, but when we got there, it was the head house that blew.
The fractured concrete that rained down on the head house control room killed 36. The shock wave from the first explosion traveled through the facility, causing additional dust to become airborne and to combust. A number of secondary explosions ignited instantaneously, completely destroying the facility.
The explosion in West Wego involved a very large quantity of dust built up in a very large structure. Due to the magnitude of this explosion, the exact cause cannot be pinpointed, but is likely a malfunctioning mechanical component on the bucket elevator, such as a failed bearing.
The resulting mechanical friction would have produced a fatal spark or enough heat to cause the dust to ignite. The West Wego disaster remains the deadliest grain dust explosion on record. In the years to follow, the grain elevator industry has taken extensive measures to minimize the potential for grain dust explosions. The Bungie grain elevator in Destrehan, Louisiana, serves as an example of new safety methods implemented throughout the industry.
The incidents of 1977 in the grain industry was kind of a wake-up call, if you will, for the whole industry to realize that we had to give a renewed focus and much more emphasis on root cause analysis of what causes these type of explosions.
One of the critical safety features implemented by the industry is to closely monitor potential ignition points, primarily the bucket elevator, the cause of 40% of all grain dust explosions. If a bearing overheats or the conveyor belt is misaligned, heat sensors located throughout the elevator legs will notify personnel of a potential explosion.
We have over 700 of these discrete points that we're actually monitoring the temperature all the time, and that information is conveyed back to the control room that is sensing these temperatures, giving us alarm if it gets to a certain level, and can even shut down the equipment automatically if it gets to a higher level.
However, if there is an accidental explosion, measures have been taken to contain the blast wave, preventing the often deadlier secondary explosions.
3, 2, 1.
How it works is that the suppression device actually senses the increase in pressure caused by the early stages of an explosion. and would dump a chemical into that bucket elevator casing that would immediately suppress and eliminate the explosion.
The chemical agent is dispersed within 80 milliseconds, stopping the explosion in its tracks. And as a direct result of the West Wego incident, grain elevator head houses are no longer located above employee offices.
Spreading the facilities out, moving the control rooms to remote locations, all of those came at a cost, efficiency, but was worth it from the safety payback.
We went from a time in a peak year over 60 people were killed in agricultural dust explosions in the late 70s, and a great reduction in risk has been achieved through the engineering evaluation of these types of accidents and taking appropriate steps based on the knowledge learned.
August 13th, 1979. The Rosemont Horizon Arena suffered a major structural failure and collapsed in the middle of its construction. They are the modern-day versions of the Roman Colosseum, built to house and entertain thousands. But engineering mistakes can lead to a disaster. In the late 1970s, arena collapses became eerily common. In 1978, the Hartford Civic Center suffered a structural failure just hours after hosting a sporting event. In 1979, the Kemper Sports Arena also came crashing down. Both arenas had a common point of failure: the roof.
And what normally causes roof failures really has two origins. When structures that have been completed fail, they fail either because they're overloaded or because there's some problem of deterioration perhaps, or some other issue where the structure's performance under load is different than the assumptions. The roofs that never make it out of construction, those roofs collapse during construction, and one of the most prevalent causes are some form of instability.
Such was the case in 1979 with the Rosemont Horizon. In 1978, the village of Rosemont, Illinois, a Chicago suburb, broke ground on an ambitious 18,000-seat capacity sports complex. The decision to build the arena was largely influenced by Rosemont's close proximity to Chicago's O'Hare Airport, one of the busiest in the world. But the airport was also responsible for a great deal of noise pollution, enough to demand a unique type of roof that utilized wood.
It is practically dead center of one of the glide paths coming in on the runways. So the wood was used for sound insulation.
A design for the roof of the Rosemont Horizon called for 16 glue-laminated arches, each spanning 288 feet.
If you can keep the arch in a single plane, like a piece of paper, it is a very efficient structural system, and one that's very strong for its weight. The thing that's important to recognize, though, is you must make efforts to keep it in plane. As soon as the arch begins to move out of plane, in other words, to twist or to rotate, it immediately begins to lose strength. It creates conditions which allows the arch to behave badly, and ultimately it will collapse.
Each arch of the roof was fashioned from 3 distinct pieces. 2 entrances were connected to 2 concrete buttresses. And then the crown truss was placed in the middle. The 2 end pieces were then spliced to the centerpiece by prefabricated metal sheeting. Running perpendicular between the arches was a series of wood beams known as purlins.
Those purlins serve 2 functions. They support the roof decking and the roof materials, but more importantly, they laterally support the arch, which is a very slender element. The arches are absolutely critically supported by the purlins.
As the arches were being assembled, problems quickly arose. The arch sections didn't line up with the splice holes. Also, the spacing between the arches was off by as much as 12 inches in one span, making the purlins difficult to place. And because of the misalignment, some of the connection holes were enlarged and many of the bolts were omitted. Temporary bolts called drift pins were used instead.
One of the principal differences between a wood structure and a steel structure relates to the connections and the bolting processes. The erectors in the Chicago area would rely on steel erectors, people that are familiar with such structures as the Sears Tower, John Hancock, and other notable steel structures. In those structures, it's common to not employ all the bolts, to put all the bolts in the connection, because of the difficulty in fitting up a multi-bolted connection. In wood, we have to be careful that all of those bolts may be necessary for our delicate friend, the arch, who has a tendency to get out of plane.
In the early morning hours of August 13th, 1979, the final arch of the roof was being erected when a 20-mile-per-hour gust of wind blowing perpendicular to the arches led to disaster.
The arches became unstable and collapsed, moving toward the west, and it formed somewhat of a progressive type collapse in which one arch failed, released the lateral bracing to the next arch, loaded it laterally, it failed, then the next, then the next, then the next.
The timber roof fell 60 feet, splintering like a pile of matchsticks. 5 construction workers were killed in the accident. The arena was completely destroyed. An investigation into the failure of the Rosemont Horizon found that 54% of the 966 required bolts were missing from the roof. Of the 444 bolts that were in place, 338 had no nuts.
The principal reasons for the collapse of the roof relate to the absence of lateral bracing on the main arch members. That lateral bracing is accomplished by fully effective connections between the purlins and the brace to make sure that the arch can't move laterally.
In the days that followed, a decision was made to rebuild the Rosemont Horizon following exactly the same design plans, but with a different contractor.
When we erected the roof the second time, each 24-foot section was completely installed and 100% complete before we moved on to the next section, which in essence allowed each one to be 100% secure before we moved the supporting structures.
The Rosemont Horizon has been renamed the All-State Arena, and it served its community for more than 20 years. One design, 2 executions. The roof failure of the earlier arena demonstrates that avoiding an engineering disaster relies as much on the diligence of the builder as it does on the skill of the architect. Grain elevators, carrier ships, coal waste dams, and modern structures. In the 1970s, they were all catastrophes waiting to happen. And all provided hard-learned lessons that without proper safety regulations, vigilant public scrutiny, and professional diligence, an engineering feat can become an engineering disaster.